Integral operators. Now, using the operator notation, we know that we have some differential operators that we deal with in physics. The first one is the gradient operator, which is this one. And if we have gradient operator shown together with a dot product, then this is called divergence operator. And if we have gradient operator with a curl, then this is called, with a cross product, this is called a curl operator. Now, similar to these differential operators, gradient, divergence, and curl, we can talk about integral operators. How can we define an integral operator? It's integral dx, after which we have a function of x. So, for example, integral dx operator applied to this function x squared x plus y squared. This is actually equal to y squared because it's just a function of x it will apply to. Integral operator dx x squared x plus y. Alright, so you can notice that the dx must come before the integrand to qualify as an operator that's acting on the integrand. So that's basically using the operator notation. Now, using the integral operator, we have several options that can generate vectors or scalars. The first one is the line integral. Line integral is the integration along a certain path. So certain path, C, let's say, and we can show it like this. Integral over a certain path, dr dot product. So this is our line integral operator, which is basically a scalar product with the integral operator. Okay, and the well-known example is the work done by a force F along the path C. We define the work as the path integral C on path C dr small displacements dot product with the force. This is our line integral, and that is to say we're going along this path following this position vector, and small displacements are shown along the path. So for each small displacement, the force is approximately a constant. So we take the dot product with the small displacements and perform this integral along this path. Now, what if it's a closed path? For a closed path, we will have the operator shown like this, the integral sign. We put a circle along the path and dr dot product. So this is the closed path line integral operator. Okay, and in Cartesian coordinates, we can write the this small displacements as dxi ei hat, so that our work done by this force, the path integral, will give us integral over the path C dr dot product with the force is equal to the integral over the path C dxi fi, because we're taking the projection of the force onto the displacement axis. So that's basically going to be in EI hat direction. And what does this yield? This yields us a scalar. So performing the line integral, we obtain a scalar. Okay, what other options do we have? We can have possibly a line integral that yields us a vector. So let's look at that version. We have an integral over the certain path C dr without the dot product. So this is going to give us a vector as an answer. So this would be acting on a scalar function. So dr acting on a scalar field, for example, acting on phi, this will give us in Cartesian coordinates EI hat the path integral C dxi acting on our scalar function phi. So this would be in Cartesian coordinates. Okay, so phi is our scalar function. Another option would be to get a vector using the cross product. So we can have a line integral C dr vector with a cross. So this will give us the line integral operator yielding a vector cross product. And in that case, if we write our operator path integral over the path C dr cross product with vector v, using our subscript summation notation, this is ek hat integral over the path C dxi v sub j epsilon I j k. All right, and this is how we would do it in Cartesian coordinates. And remember, the repeated index implies summation. Okay, so in subscript summation notation. All right, so we've talked about integral operators. First of all, we have the familiar differential operators, the gradient operator, divergence operator, gradient with the dot product, gradient with the cross product gives us the curl operator. Similarly, we can define an integral operator, integral dx, and this operator can act on a scalar function, for example, and give us the operator only acting on the function, the parts of the function that's function of x, and the dx must come before the integrand so that we can write it as an operator in operator notation. So what are some possibilities with these integral operators? So we will start with line integrals. It's the integration along a certain path C. We can use it with a dot product. For example, the dot product of displacement with the force gives us the work done by that force on the system. And for a closed path, we would put a circle here in the integral sign to indicate that it's a closed path line integral operator. In Cartesian coordinates, our displacement vector can be written as dxi ei hat, so that over the path C, dr dot f becomes dxi fi. That is to say, we're taking the ith component of the force, and this integral yields a scalar. On the other hand, we can also have line integrals that yield vectors. We can do it either by not introducing the dot product, simply just taking the integral over the path C dr times the scalar function f, which would give us ei hat integral over the path C dxi phi in Cartesian coordinates. Or we can use it with the cross product vector cross product. So this would give us integral over the path C, dr vector cross product with vector v, and using subscript summation notation, this is epsilon ijk dxi vj ek hat. So that's how we can write it in subscript summation notation. And then we will also talk about other forms of integral operators. We can use them as surface integrals, we can use them as volume integrals. So that will be in the next video.